our presentation today is on the variational deep embedding. It's a unsupervised and generative approach to clustering. And my name is Angel Comos, and I'm presenting with Harsha. Let's dive right in. So variational deep embedding is a unsupervised generative approach, and it's within a framework that's used called the variational autoencoder. And so the motivation of this work is to be able to develop a clustering model based on neural networks that can learn good representations or the latent variables of a data set, and then also be able to generate samples. So if you look at this figure below, we have a number of pictures of faces that were generated, and we have features, let's say the color of the hair or the way the person's looking, their orientation, maybe the color of their eyes. And this neural network or this framework can come up with a new generated model based on those latent variables. And so we have to talk about what a latent variable model is. So what we would like to do is be able to generate a data point, which would be the marginal distribution or X, and then use a prior distribution or the latent variables, let's say those features that we described in the intro, and be able to map how those latent variables will actually drive the generation of those data points. And then on the other way, we want to be able to perform inference where we use the original observed data, and we can come up with a series of latent variables. So we use a posterior distribution to describe how latent variables, can be produced by those specific data points. And so the variational deep embedding models this generative process by using a Gaussian mixture model for clustering, and then a deep neural network that is based on the variational autoencoder. So a Gaussian mixture model can take a series of points and then assign new distributions or a number of Gaussians to those points based on their statistical distance relative to each distribution. And then the variational autoencoder is much like an autoencoder, but we're trying to encode the latent variables by using statistical information like the mean and the standard deviation of the data that's encoded. So we're talking about this problem about clustering, and there's a lot of different clustering methods, and here are some of the clustering methods that are used in literature pretty frequently. And so, there's two major categories of clustering where, we have similarity-based clustering, which would be something like spectral clustering. And then we have feature-based clustering where, we have clustering methods like the k-means or the Gaussian mixture modeling. So although k-means and Gaussian mixture models are, used extensively, learning good representations that's most suitable for clustering tasks in deep neural networks is left largely unexplored. And that's one of the topics that the variational deep embedding tries to address. So the general approach to the variational deep embedding is that it acts as a clustering framework. And this framework models the data generative process by choosing a cluster from the Gaussian mixture model then sampling a latent representation Z, and then using a deep neural network, or in our case, a variational encoder, to decode to an observation. And so the variational deep embedding is optimized by using a deep neural network to encode the observed data into latent embedding. And we can use the stochastic gradient variational Bayes to maximize a statistical measure called the evidence lower bound. And that's kind of how we are able to associate an observed model with the statistical priors that drive the latent variables. And so here's a flowchart of the framework. First, we pick a cluster from our Gaussian mixture model, and that would describe the mean and the standard deviation of that cluster. And then we then generate a latent embedding where the pi sub k is the probability that we choose the cluster. The latent variable is a learnable parameter, which then would then describe the latent variable. And that gets passed into a decoder network, which then can be embedded into an observable X, or let's say it's an image or a digit in the MNIST data set. And then that's fed back into the encoder network, which is then used to update the mean and the standard deviation of that cluster. So it's constantly trying to shift the weights of the mean and standard deviation of each cluster within our data set. And so we have to also look at, how can this variational deep embedding generate data? So we suppose that there are K clusters in our data set, and we want to generate an observed sample X from a range in that dimension. And so first we choose a cluster, and then we choose a latent vector, which would describe the cluster in terms of statistical measurements, the mean and the standard deviation of the cluster. And then for our case, we would like to look at real values. So we would like to compute the mean and the standard deviation by passing this in that information into a deep neural network F. So the forward pass would work on the latent vector. And so according to the generative process, we're trying to find the joint probability of X, which is the observed data, Z, which is the latent vector, and then C, which is the cluster. So what this shows is that if we have P given Z, which is the probability that an observed data point is generated based on a latent vector times by Z given C, the probability that we've generated a unique latent vector based on the cluster we've selected, and then multiplied by the probability of C, which is the probability that we choose a specific cluster from our data set. So what happens is when you perform a variational autoencoder, you're actually creating a deterministic or a random bottleneck. So you have to perform a reparameterization trick. And so what this allows us to do is it allows us to train the latent vector in a back propagation step. So we separate our random node by using epsilon, which is a fixed stochastic node, thus moving our random node from Z into the epsilon value, which then is used to create a latent vector Z. So this allows the network to be able to use back propagation on the standard deviation and the mean of what we're trying to learn as far as the latent vectors that would describe our network. So this leads to the variational lower bound. And so the variational lower bound is, we're trying to maximize the variational lower bound of the network. And so this lower bound describes the likelihood, or the likelihood that our variational posterior is approximately close to the posterior probability. So we're trying to basically find a distribution that would minimize the KL divergence. The KL divergence is basically a statistical distance that shows how similar two probabilities are. And so when we maximize the evidence lower bound, we generate a probability or a distribution that best estimates how the observable data maps back to our latent variables. And so here's a quick animation of how we have a true posterior, which is the purple curve, and then a surrogate distribution. And as those two distributions start to overlap, we actually maximize the effective lower bound. And so what that allows us to do is it allows us to say how likely our latent variable can actually predict or generate an observable X based on the clustering that we've selected from. On that note, I'm going to pass it off to Harsha, so he can describe.
Sorry, excuse me. Can you explain what is this two curve? I cannot see the legend clearly. So
sorry, yeah. We had some, I guess, downsampling when we created this. So the purple curve is the true posterior, which is the distribution of the observable that we want to basically figure out, right?
Okay.
And then the red curve is a surrogate curve, which is a distribution that we're trying to learn, where based on how our, our latent vector generates, let me take a step back. So the surrogate is a distribution that would then map how an observable X would be generated. And so we want to be able to say our true posterior, which is the distribution of our observable data, is very close to the surrogate, which is a generated distribution. Did that explain?
Yes, yes. And how about on the left, you turn like two things? I also cannot see.
Yeah, so we're tuning, so the mean of the surrogate.
Okay.
Excuse me. We're tuning the mean of the surrogate and also the variance.
Oh, okay, good. Now I get it. Yeah. Okay, good.
So now the red curve is very similar, and the statistical distance is becoming smaller. So that then increases the evidence lower bound, which is the loss function of the network.
Very nice. Okay, good.
So I'll pass it off to Harsha, and you can discuss some of the interesting results that we find in variational deep embedding.
Okay.
Can you move to the next slide?
Sure.
So I'm going to talk about the evaluation metrics. Just give me a second. I'm not able to see the whole screen.
Sure. No problem.
Yeah. So I'm going to discuss about the valuation metrics that we are using in this paper. So the most common MNIST data set, which has 70,000 samples and which has 28 by 28 pixels. So the input dimension is going to be 784. And the classes are going to be 0 to 9. So 10 clusters are obtained out of the VADE network. So the other benchmark that we are using is heterogeneity human activity recognition, which is basically nothing but the patterns generated from smartwatches, and smartphone devices. They basically generate some patterns based on the activity like jogging, like walking. So based on those activities, the patterns are generated. So that's the HHAR data set. So reuters 10K and reuters data set is the data set which has all the news articles in it. So it is organized as documents. So each document has several sentences. So the several sentences has several words in it. So each word represents a class. So when we try to input a sentence to the network, so that the output the VADE tries to organize the words, the frequency of the words used in a sentence or in a document. So STL is the data set. It's a digital image data set. It's a color image data set. So it is of 98 by 98 pixels. So it is inspired from CFAR10 data set. So the table below represents the samples, the total number of samples used, and the dimensions of each and every data set, and the number of classes that we are trying to cluster. Yeah, next slide, please. Next slide. Um, I just want to show you how the MNIST data set and all the data sets looks like. So it is basically handwritten images and 28 by 28 pixels, the 0 to 9 classes. Yeah, you can go to next slide again. Next slide, please. So this is the XTL data set. Okay. This is the STL data set where you can see all the digital images, all the color images. So the aeroplane, all the top section represents the aeroplane. All the top section of the image has all the aeroplane images, the bird images, car, and all such kind of images. This way the classes are divided. Each pixel is 98 by 98. Yeah, next slide. So this is the HHAR data set. So the left portion of the data set represents the patterns, and the patterns are the patterns of a person are transmitted to the network. So then the output layer clusters each and every pattern into different sections, like downstairs represents a class, jogging represents an activity. These are different activities on the side, and yeah, these are different. This is a kind of data set. Yeah, you can go to the next slide. So this is the reuters data set where it has 810,000 English news stories with a lot of classes. The right side image shows you the classes, the words in that data set, and with all the frequency of the words used in the documents over there. So because there are a lot of classes, we are not going to use those number of classes. We are just dividing the whole data set into 4 classes, and we discard all the sentences with classes which doesn't with the classes that doesn't have these words in it. So the 8,000 and 810,000 news stories are minimized to 685,000 article data set. So that's the whole reuters data set, and the reuters 10,000 data set is selected from the 685,000 data set. 10,000 random documents are selected from the 685,000 data set. So yeah, that's the reuters data set. Can you move to the next slide? Previously I was discussing about the data sets that we are using for evaluating the performance. Now I'm going to discuss about the clustering methods, different types of unsupervised clustering methods. that we are going to compare with the VADE network. So the first one that we are going to compare is the Gaussian mixture model, which Andrew was talking in the previous slides. So the second cluster unsupervised clustering method is the autoencoder plus Gaussian mixture model. So it is nothing but it is basically a VADE network, but without the divergence term in it. So the because of not having the divergence term in it, the error rate is going to be minimum for AE plus autoencoder plus Gaussian mixture model. So the next clustering model is VAE plus GMM variational autoencoder. Yeah, even this is similar to the similar to the VAD network that we are trying to implement here. So, but this network doesn't have any optimization of VAE and GMM in it. So that's that is a reason why the error rate for VAE and GMM is going to be minimum compared to VADE. So adversarial autoencoder and LDMI, local discriminant model and global integration, and DE's deep embedding clustering are different various kinds of clustering unsupervised clustering methods that we are trying to compare the VADE with. So the fact that VADE outperforms AEGMM without KL, which doesn't have the KL divergence term in it, and VAE with the GMM significantly confirms the importance of regularization term. So this is the lower bound equation. So the right portion of the equation represents the regularization term, and the left portion of the equation represents the regularization term, and the right portion is the KL divergence term. So the AE plus GMM doesn't has the regularization, the divergence term, and the VAE plus GMM. In VAE plus GMM, the regularization term is not properly optimized. And yeah, that's what this slide is about. Next slide, please. So you can see the error rate comparison graphs in this slide. So the plot here represents the accuracy versus number of epochs of various clustering methods that we have discussed in the previous slide. So from this graph, we can clearly see that the clustering accuracy of the VAD, which is in the blue colored shape, is maximum. It outperforms all the clustering methods, all the previous clustering methods that were discussed. Yeah, these are, and one more thing that we can observe from the graph is the DEC, AEE, and LDMI and the GMM clustering methods show better show good performance, and it doesn't depend on number of epochs. The accuracy remains constant for all the epochs, for any number of epochs. But for VADE, we can see that by increasing the number of epochs, the accuracy is going to be increased. But for these four clustering methods, the accuracy is going to be constant. This is the equation on the left represents is used for calculating the accuracy here, and where LI is nothing but the ground truth label, and CI is the clustering assignment, from the clusters that are obtained, and MI is NM is set of all possible one-to-one mappings between cluster assignments and labels. Yeah, next slide. Oh, so the benchmark that we are trying to use for calculating the error rate is MNIST dataset. So VAD, this is the initial epoch. This is going to be the initial representation of the cluster data in the latent space learned by VAD during the training on MNIST dataset. So this is the initial state on the epoch 0. So the clustering accuracy at this point is going to be 11.35%. And yeah, as you move on, as you try to increase the number of epochs, the representation becomes much better. Yeah, for one epoch, the clustering accuracy is going to be 55.63, and you can move on. Next slide. Yeah, this is for 5 epochs, 72.40. They're trying to the representation becomes better and better. Yeah, next slide. Yeah. So this is for 50 epochs. The clustering accuracy is going to be 84.56. As you can see, the classes, the different classes are getting segregated from here. As we are trying to increase the epochs, the accuracy is also going to be increased. Next slide. So this is for 120 epochs, which has 90.76% accuracy. Yeah, next slide. This is the after iterating all the epochs, the maximum accuracy that we could achieve is 94.46 for the MNIST dataset. So this is for VADE network for that, and yeah. So because it is an MNIST dataset, you can see 10 different clusters, 10 different colored representations here. Yeah, and yeah. As we move on to next slide, the clustering, the table here represents the clustering accuracy performance comparison on all the data sets. So previously we were trying to calculate the accuracy just based on the MNIST data set. So this table represents the accuracy obtained for different data sets for different clustering methods. So as you can see in the table, the bottom portion VADE has the maximum accuracy, and it outperforms all the clustering methods for all the benchmarks. For MNIST it gives 94.46, for HHAR it gives 84.46, and yeah, it outperforms all the clustering methods. Yeah, and because VADE is an unsupervised model, comparisons are not done with the supervised models. So all the models that we are that are represented in that are shown in the table are the unsupervised models, and we are not comparing with the supervised models. And the learning rate for MNIST, HHAR, Reuters 10K, and STL10 is going to be 0.002. And it decreases every 10 epochs with a decay of 0.9. And the learning rate for Reuters is 0.005, and with a decay of 0.5 for every epoch. That's for 10 epochs, but for Reuters it is for every epoch the decay rate is going to be higher. Yeah. Yeah, this is actually the same. Slide that we had, and the sample generation. So the major advantage of VADE over DEC, deep embedded clustering, is that it is by nature, it is a generative clustering model. It is used for representation, and it is also used for generating any denoised image, or generating the image from generating the embedded image itself. So as you can see here, these are the different unsupervised clustering methods: GMM, VAE, and VADE. So the left portion represents the GMM model. As you can see, the GMM is doing the regeneration, but the image has a lot of noise in it. But when you go to VAE, the generation is good, but it's not performing clustering over there. So the data on each and every row are not organized. They are scrambled, but the generation is perfect. But when you come to VADE, it is doing the regeneration with highly realistic samples for any specified cluster. The clustering accuracy is also great, and also the performance of VADE is comparable with Infogan, which gives a similar output. Yeah, and can you move on to next slide? So in this slide, we are going to discuss about the impact of number of clusters. So to demonstrate VADE's representations power as an unsupervised clustering model, we deliberately choose different number of cluster K values. So MNIST dataset has 10 classes. But if we give 7 as the clustering, 7 as the k value, as you can see in the left figure, that the last 2 rows are kind of messed up. The 8 and the 3 are organized in the same are in the same row, because 3 and 8 looks pretty much similar. So and we are trying to use seven clusters. So and then the 9 and 4 looks a little bit similar. So that's why it is in the same row. So yeah. So because we are doing feature-based clustering, we don't have to worry about the distance between two images here. So based on that, the clustering is happening here. So on the right side, when we give clustering k value, which is equal to 14 greater than the number of classes. So for MNIST dataset, the classes are 10, but if you give 14 as the cluster value, so it's going all different kinds of even though it is a 1, it is because there are some minor feature differences, like as you can see, the one on the first row and the ones on the 4th row are kind of different because they are tilted and they are upright, and the zeros, you can observe the zeros on the right side, right picture, that some zeros are thin. The thin zeros are in a different in a different row, and it is organized in a different cluster, and the fat zeros are organized in a different cluster. Next slide, please. So the future work with this thing is we need to know that although mixture of Gaussian prior for VADE is used in this paper. So the Gaussian mixture prior to the VADE is used in the paper, but other mixture models can also be adopted in this framework. So that's the future work that the authors are trying to implement. So instead of Gaussian mixtures, we can use different mixture models. So that's what it is about. And yeah, thank you.
So
yeah,
let's open the floor for questions.
Yeah.
All right, so let me make some comments about this. So about the last slides, you said like the future work maybe instead of like a mixture of Gaussian, maybe you can use other like mixture model. So is that the claim of the author, or is that what you thought? Like what you think it should be the future work?
Yeah, that's the claim of the author. I didn't come up with that. I'm sorry.
Yeah, I'm thinking about why, because like what's the advantage of using other mixture model here? So because like mixture of Gaussian is very, very popular, and if you want to, so that's why people every time when you use it, you probably the first model you think of is the mixture of Gaussian. So if you want to use some other mixture model, I would like to have some explanation, like why do you want to use that? What's the advantage, and what's the situation you want to use that prior, so it can help you to improve performance. So since the author doesn't mention that, how do you think like you use that other model? What's the application?
Yeah, the advantage maybe the accuracy that we are having with the maximum of accuracy is about 94.46, right? So maybe if we use other mixture models, maybe it can improve the accuracy.
I highly doubt it, actually. Yeah. So because like usually the reason we use that because this gives us the best result. I think possibly one explanation is for some particular like application. So they have they are not looks like Gaussian, and maybe that other model is more suitable. But I think like probably this is not a very good like we can claim this like a future direction.
Okay.
I mean, I guess
is that all the experiments? Did you implement any of this experiment here?
No, we did not. We were looking through some implementations to get a better understanding.
Okay.
But yeah, we weren't able to get the model or perform these implementations ourselves at this moment.
Because for now, I think like this, the most similar work to this one is the VAE plus the GMM. So these two work are very, very similar, and the author claimed that the result in this one, because this has like, the regularization term, and because of that, this paper performs better than the VAE plus GMM. So if I would like to see if you can do some experiment of this too, like to see if that is really the result or not. Because when someone proposes some idea, they usually claim that this idea is the best, but does it really work or not? So I would like to you guys to try, like if you can, like you don't need to maybe not implement this by yourself, but I think you can find the code of VAE plus GMM.
Yeah.
And also, does the author publish their code? So if so, you can just compare this two, like make a fair comparison. So like as a third party, so we can make a more fair comparison of these two methods, like whether this regularization term really works or not.
Okay.
Okay, that is, and another thing I want to like is at first when you first explain the idea, you mentioned the k-means and the variation autoencoder, right? So I think I really like the first several slides when you explain the idea. It's very clear. So I really like that part. So the only thing is when you first introduce this VAE, although the VAE is not proposed by this paper, I still want you to explain that a little bit, elaborate as a prior knowledge so people can understand what is VAE. So for example, you can think about that, why we use VAE here, why we want the randomness and the stochastic thing sampling here. Is that is that only because we want to generate some sample, or like it can really also help to improve the representation learning, like the accuracy? So for example, how about this? So why we use VAE? Why just use the autoencoder, right? So what's the advantage of VAE compared to autoencoder? So can we use the autoencoder as a baseline here?
Yeah, so VAE would encode latent variables, whereas an autoencoder just kind of blindly compresses the data. So using statistical information to try to drive how the model learns a feature, like for instance, we go to this image here, we have the fat, thin, upright, and oblique features. So when we use the variational autoencoder, we're trying to learn these latent representations. Whereas, when we just use the generic encoder, it may not actually learn any type of lower dimensional information.
I mean, like the autoencoder can also learn the lower dimensional information, right?
Yeah, so maybe I need to just refine, how I truly understand the variation.
Yeah, I would like to see that in your report. So I would like you to take a look at that and explain that in your report to make this more clear. Okay, overall, this is like a very nice presentation. Like I like it.